Welcome to The Explainer. Today, we are unpacking something huge, a massive multi-sector technological leap happening right now in India. We are looking at this fascinating real-time shift. They're moving away from relying on imported tech and fiercely driving toward native innovation. It's a revolution that literally spans from the microscopic architecture of computer chips all the way up to the massive roaring engines of orbital rockets. We've got some absolutely incredible source material to guide us through this today, so let's just get right to it. Think about this for a second. How do you actually build a space station, right? I mean, it sounds like pure science fiction, but the reality emerging from our sources today is that you don't just build it the old-fashioned way anymore. You print it, and you crowdsource the research to actually make it happen. So we're going to look at exactly how a futuristic machine like that gets built from the ground up, and we'll start with the very physical foundation of spaceflight itself. Okay, Section 1, Printing Next-Gen Rockets. This is the muscle of India's space program. Let's dive right into this staggering shift in manufacturing. Historically, if you wanted to build a rocket engine like the PS-4 used in the Polar satellite launch vehicle, it meant conventional machining, lots of welding, a really complex multi-step process. But ISRO's Liquid Propulsion Systems Center totally redesigned this engine using a concept called design for additive manufacturing. Basically, they used a specialized 3D printing technique called laser powder bed fusion, and they pulled this off with their Indian industry partner Wipro 3D. The efficiency gains here are just jaw-dropping. By 3D printing the engine, they took what used to be 14 separate parts and reduced it down to just one single piece. One. That completely eliminates 19 weld joints. But get this, here is the real shocker. Conventional manufacturing required 565 kilograms of raw forgings and metal sheets. The 3D printed version, it uses exactly 13.7 kilograms of metal powder. I mean, that is a massive, massive reduction in material waste. Oh, and it also cuts overall production time by 60%. And the crazy thing is, this isn't just theoretical. Back in May 2024, ISRO actually hot-tested this 3D printed engine for over 600 seconds, a full duration test. And they absolutely are not stopping there. They've done recent subscale tests on a new high-thrust liquid oxygen-methane engine, which also successfully utilized 3D printed chambers reaching immense pressures, like 56 bar. So yeah, the muscle of this program is getting stronger and it's getting incredibly efficient. But of course, muscle is pretty useless without a brain to control it, right? So let's move to Section 2, Homegrown Photonic Chips, the brain.
So the key phrase you need to know here is Silicon Photonics. Now, traditional computer chips, they use electrical signals to process and move data around. But Silicon Photonics, this is a cutting-edge frontier that literally swaps out electricity for light, photons. This enables ultra-fast computing and communications, and it does it with incredible energy efficiency. Guys, this is the absolute bleeding edge of global technology. It is absolutely crucial for everything from artificial intelligence to next-generation telecommunications.
Now, what's really interesting about this is that these tools are entirely homegrown. Unveiled at IIT Madras, this suite includes a process design kit with over 50 verified components. That means domestic engineers can actually design advanced photonic chips themselves. They also launched a universal programmable test engine for these modules. This whole initiative is supported by the Ministry of Electronics and Information Technology, and it really pushes India's capabilities right up to global state-of-the-art standards. And the ultimate goal here, moving forward under the India Semiconductor mission, is to establish a dedicated Silicon Photonics fabrication facility right inside the country. We're talking about total technological self-reliance. But, this naturally raises a pretty critical question. You have the advanced manufacturing capabilities down, and you've got the foundation for these next-generation chips. But who is actually going to do the R&D? Who is going to sit there and solve the hundreds of granular engineering problems required to make all of this actually work? Well, the answer is in Section 3, Crowdsourcing Space Research. This is the nervous system of the whole operation. See, ISRO doesn't actually tackle every single problem alone. They use a program called Respond to basically crowdsource highly specific research challenges directly to academia. There's this newly released document, the Respond Basket 2025, and it's this massive list outlining the most urgent R&D areas they need for future missions. In fact, since 2018, they have identified 871 specific research problems and just handed them out to academic institutions across the country. The 2025 edition, in particular, heavily focuses on reinforcing prototype development and pushing up what they call technology readiness levels. It is honestly just a brilliant way to upskill the workforce and make sure the next generation of engineers is already tackling real-world space problems before they even graduate. To give you a sense of just how diverse and really how fascinating these problems are, let's just look at a few requests from the Vikram Sarabhai Space Center's list. They are actively asking universities to help them develop solar paint. Yes, literally paintable solar cell technology. They want AI-powered analytics to figure out how to requalify and reuse avionics from recovered rockets. They're looking into energy harvesting using tribal electric nanogenerators, and even using quantum computing algorithms to solve complex fluid dynamics. The sheer scale of the innovation they're asking for here is absolutely breathtaking. And this brilliantly illustrates how all these pieces fit together. Which brings us to Section 4, India's interplanetary ambitions, putting it all together. So all of this innovation ultimately leads to the big payoff. Why does all this native innovation matter so much in the first place? Well, because of goals exactly like this. The Bhartiya Antariksha Station. ISRO is planning to establish its very own space station, and you simply cannot rely on imported parts or foreign supply chains for a project of this magnitude, right? It's too strategically important. You have to be able to design the microchips, you have to test the life support, and you have to print the rockets right at home. And it really all comes back to the human element. The technologies we've been exploring today, they are the very foundations preparing India for the Gaganyaan continuation missions. Because to safely put humans into space, and more importantly, bring them back, that requires the absolute peak of material science, computing, and propulsion. And the roadmap laid out in our sources is just staggering. The Respond Basket document explicitly notes that all of this preparation is building up to an incredible sequence of events over the coming decades. We're talking the Chandrayaan-4 moon sample return mission, a Venus orbiter, and ultimately a human landing on the moon. It is truly an incredible transformation to witness. I mean, we've seen the journey from a reliance on conventional, heavy manufacturing all the way to literally printing engine parts in a matter of days. We've seen the shift toward designing light-speed microchips right on university campuses. So we want to leave you with this final thought. With rockets printed at home and chips designed on campus, what limit is truly left for India's space ambitions? Thanks so much for joining us on this explainer, and we'll see you next time as we keep unpacking the ideas shaping our world.